Okay, so we are at friction on connected particles. Two particles, P and Q, of masses 5 kilograms and 10 kilograms respectively, are connected by a light, inextensible string. What does it mean if the string is inextensible? Okay, so it means that it doesn't stretch. What does that mean about how we do things in our calculations if the string doesn't stretch? The tension is the same, but the thing I think perhaps we use more often is that the two particles will be accelerating at the same rate, or they will be moving at the same rate, because the string isn't stretching, so they have to be moving at the same time. It then says the string passes over a small, smooth pulley. What does it mean if the pulley is smooth? It means the pulley has no friction. What consequence does that have on our model? What does it mean about the tension? It's the same on either side of the pulley. Remember, if the pulley was like rusty or something, one side might snag more than the other, so one side's tension might be higher than the other one. Anyway, it's a rough plane. P rests on the inclined plane, and Q hangs on the edge of the plane with the string vertical and taut, basically as we see in the diagram. It hasn't said that Q is touching the plane. If Q was touching this wedge side here, there'd be some friction and normal reaction, but we never really do questions that look like that. There might be, like, very rarely something kind of like touching the other side of it, but we're not going to be looking at those kinds of scenarios generally, okay? The plane is inclined to the horizontal at an angle of alpha, where tan alpha is 0.75, as shown in the diagram. The coefficient of friction between P and the plane is 0.2. The system is released from rest. Find the acceleration of the system and find the tension in the string. So the first thing I probably always like to deal with in these questions, if I see that tan alpha is 0.75, obviously 0.75 is our 3/4, I like to draw my triangle and say, well, that's my opposite and adjacent because of tan. So I get that sine alpha is 3/5 and cos alpha is 4/5. I don't know why, I just always like to do that at the beginning of the question rather than later on. I'm then going to look at this diagram and I'm going to add in some of the forces that we've got here. Now, the best thing that you should be doing when you're not sure about directions of forces is you should literally be imagining that you are a block, that you are the block sat on the slope, right? First of all, we're going to imagine, though, that we are particle Q, and I want you to imagine that you are a block and you've got a rope coming out the top of your head and you're like hanging there. What does it feel like if you're that block with a rope coming out the top of your head? What did you say? So what does it feel like, Sadia, if you're that block? You feel like you're being pulled up. Great. So that must mean there is a force pulling you upwards by the string. What else do you feel if you're that block hanging there? Yeah, you don't feel as light as a feather. You're a block. You're heavy, right? So you also feel your weight pulling you down like this. 10 kilograms is not fat. 10 kilograms is not alive, or a baby. Maybe not a baby. Okay, now if you imagine that you are the particle P and you're sat on the slope, it's a very odd subject, really, when you think about it. You're sat on a slope. What does it feel like if you've got this rope coming out of your chest up the slope? Yeah, it feels like the rope is trying to pull you up the slope, yeah? What else do you feel like if you're sat on that slope with a rope coming out your chest? Pardon? Yeah, no, say it, because it's good. This is how teaching works. You've got to talk to me. You may be sliding down, okay? If you're sliding down, what would you feel on your block bum? Friction. You'd feel friction, right? But why are we excluding that bit? But because it's better to imagine these things, because in the next slide I'm going to ask you to imagine something different again. But do we think that block P, which is called Sadia at the moment, does Sadia think she's moving up the slope or down the slope? Probably down. Which one in this case? I think that it's going to be moving up. Now, sometimes there are some rare situations where Sadia could have been moving down the slope, in which case the friction would have been going up the slope. But in this particular case, Rayhan's block is far heavier. So yeah, it's probably going to be moving up. And if you ever did get it the wrong way round, you'd get some negative values and you'd have to probably redo some of the questions. So we think that this one is going to be moving to the right, which must mean we think that this one here is going to be moving downwards. So I'm just saying the acceleration like that. If it's moving to the right, then we're going to have the friction going to the left. What else does Sadia feel when she's sat on that slope? But she feels the what? The resistant force. The resistant force is the friction.
I mean the reaction force.
She feels the reaction force. On the block backside, there's a force pushing upwards, and I presume she also feels that she is not light as a feather. She also feels her weight that we've got there. Now, you don't obviously have to think all of those forces. The only thing I do it for that's actually important is tension, because people sometimes get the idea of tension wrong. So it's just a way of imagining it. And it's going to be particularly important in a second. I'm going to get you to imagine that you're a pulley and what it feels like to be a pulley. Okay, so we're going to get on with this question now that we've done a bit of a strange beginning. We'll resolve the forces. So we'll have our 5g cos alpha and our 5g sine alpha looking like this, okay? Now, we've got two different particles that are happening here, and we've already talked about the fact that because the string is inextensible, the particles must have the same acceleration, which is going to be useful because we're going to have two equations, and we're going to try and solve those equations simultaneously. What we will start off by doing is we will start off by writing an equation of motion for the second particle q. What do I mean by an equation of motion? Not Suvat, no? It means F equals ma. If you ever see an equation of motion, it actually means to do F equals ma. And we think that Q is moving downwards, so we're going to look downwards. The reason I'm telling you this phrase, equation of motion, is because it probably, in an exam question you'll come across, it will say, write down an equation of motion for P. And it literally just means do F equals ma. So I want you to be aware of that language. So what's the equation of motion that we have for that particle? Yeah, it's just 10g, the force is downwards, minus the resistant force, which is the tension, which is equal to 10a. Now we're going to do an equation of motion, but we're going to this time do it for p. Now, obviously, you could draw the additional diagram that we need there. But actually, before we do that equation of motion, because we've got friction, what do we usually do first when we've got... Good, we're going to find the normal reaction for p, because if we have the normal reaction, we're then going to be able to deal with the friction. So we obviously are going to need to find that bit first. So we're going to resolve in that direction. The normal reaction R is equal to what?
5g sine cos.
5g cos. This is where maybe the extra diagram should be drawn. I'm just trying to save a little bit of time. So we get 5g cos alpha. But cos alpha is 4 over 5. So R is, 5g times 4 over 5. Which is just 4g. So now we know what R is, we can actually do the equation of motion that we've got for this particle P, right? So remember, it's moving in this direction. So the only force that we've got going to the right is T. We've then got going resisting it, we've got 5g sine alpha. And we've also got mu R, and that is equal to its mass, which is 5, times its acceleration. There's probably a bit of simplifying that we should be doing here, because we know that sine alpha is 3 over 5, and we know that mu is 2 at 0.2, and that R is 4g. 5g times 3 over 5 is 3g. 0.2 times 4 is 0.8. So this is minus 3g minus 0.8g, which is just minus 3.8g, which is equal to 5a. Do you notice how I've just kept it in terms of g? A couple of people in the other class were like, great, I know what g is. I'm going to find out what those numbers are. But because it's just in terms of g, it's a little bit easier to deal with if we just leave g in and just deal with it at the end of it. So I've got an equation of motion. Whoops. That's a terrible highlighting colour, right? I've got an equation of motion for that particle, and I've got an equation of motion for this particle. The thing that allows me to solve these simultaneously is that the acceleration is the same. Why is the acceleration the same? Because the string is inextensible. Why is the tension going to be the same? Because the pulley is smooth. Okay, so it's important to remind ourselves why we're actually allowed to do simultaneous equations here. Now, there are many different ways you could solve these simultaneous equations, but there's always going to be a quick one for these. I'm going to call this one equation 1 and this one equation 2. Any suggestions of the quickest way of solving these? You could just add them together. If you want to do rearrange and make t the subject and substitute in, that's perfectly fine. But you'll notice there's always a minus t and a plus t, so those t parts are going to cancel each other out. So when you do equation 1 plus equation 2, you get 10g minus t plus t, so they're going to cancel, minus 3.8. So you get 10g minus 3.8g equals 15a when you add the 10a and the 5a. So that's 6.2g divided by 15 is the acceleration. And now is either we want to keep that as a fraction, or let's find out what it is as a number. So we get 4.05 meters per second squared to 3 significant figures. Nothing really new, but just a reminder of pretty much what connected particles was like when you did this in year 12, right? Hopefully this is going to iron out some of those misunderstandings or things you weren't so sure about in year 12. These are usually maybe 5, 6 marks, because there's quite a lot. You get 3 marks for actually just doing the equations of motion, but because there's so much in here, there's probably another 2, 3 marks in it. So it's quite a lot, probably 6 marks, and we haven't even finished it off yet. So we found the acceleration in the system, and now we want to find the tension in the string. Yeah?
You know, if like initially you get your diagram wrong somewhere, like a little piece of it, you still get the arrow carried forward?
No. Because that's a really, really good question. So you would get the method mark for knowing you're trying to do F equals m aim. But let's say, if we talk down here, let's say you got sine and cos the wrong way around, you'd get the method mark for doing it, and then you'd lose the accuracy marks. So it is so important. Mechanics isn't about this kind of stuff that we have down here. Mechanics is about this and this. Those 2 lines that I've put stars next to, if you wrote those ones down, you've basically like vacuumed up all the method marks and most of the accuracy marks just in writing 2 lines of working. So it's really important you spend time making that diagram absolutely perfect rather than rushing, okay? Last bit, I want to find out what the tension is. How am I going to do that? Sub it into the equation. Which equation do we think is going to be easier? I personally think this one is easier, because to find out what t is, you just do the acceleration times 5 plus 3.8g. But it's just a preference. You can obviously use any of them, but anything that avoids negatives, I find, is probably a preference for me. So we're going to use 2, equation 2, and we can see that t is equal to 5a plus 3.8g. Now, I wouldn't use 4.05. I would use whatever value I had on my calculator just to keep it as accurate as possible. So I'm going to times that by 5, and I'm going to add 3.8g. And I believe the value of the tension is 57.5 newtons to 3 significant figures. Okay? If you have a question where the particles are, oh, sorry, I'll leave it down there. Well, I don't need to see the diagram. If you have a question where instead of it saying 5 kilograms and 10 kilograms, it says like m and 3m, your acceleration will always be a number because the m's will cancel out, but the tension will always be in terms of m. And that makes sense because we know acceleration often doesn't have anything to do with the mass of something, but the tension will do. If you imagine that those blocks were 3 grams and 3 grams and 10 grams versus 300 kilograms and, I can't remember what I said, 1,000 kilograms, the tension in the string is obviously going to be varying according to the mass. So you may have some questions where the tension ends up with an m variable in it. That is perfectly fine. Your acceleration will not have an m variable in it because the m's will cancel. So next question I'm going to do pretty fast. The first half, part A and part B, will be quick, because really the next example that we've got, which is the last part of this topic, is all about part C. That's the whole thing that is new in this second question that we've got there. So I'm going to go on to the the next page in just a second. I can put it back on the other slide, on this slide afterwards, maybe. Okay. Is that a question you mean? No. Okay. So I'm going to go pretty quick on this. Light inextensible string is attached to a block A of mass 2 kilograms. The block A is held at rest on a smooth fixed plane. Well, you're probably not going to get one of those in the exam. This is really because I'm wanting to explore what part C is, where we're talking about this resultant force acting on a pulley. So it's a smooth plane, angle of 30 degrees. It says the string lies along the line of greatest slope of the plane. All that is saying is that the string is going straight up the plane like this, not going at some kind of random angle, and it just looks like it does in the diagram. Smooth light pulley, which is at the top of the plane, blah, blah, blah. The other end of the string is attached to a block B of mass 5 kilograms, blah, blah, blah. The system is released from rest by modelling the blocks as particles and ignoring air resistance. Okay, there's just nothing interesting in that whole passage, but it's important you do read it. So I'm going to add in my diagram. I get my 5G, and I get tension upwards. I get tension to the right. I get the weight coming down, and I get the normal reaction going over like this. But there's no friction because the slope is smooth. So this is going to be a much quicker kind of question. Part A says, show that the acceleration is 4/7g and find the tension in the string. The reason these are part 1 and part 2 is because they're the answers to the simultaneous equation. And sometimes when people solve simultaneous equations, they might find the acceleration first, or they might find the tension first. So if you actually end up finding part 2 before you find part 1, it doesn't matter. So if you ever have a part 1 and part 2 as like sub-parts of the question, the order of what you answer them in doesn't matter, okay? So I'm going to do an equation of motion. I'm going to do F equals ma. It's always easier to start doing it for that B particle, the one that's hanging there. So my equation of motion would be what, Sufyan? Is equal to 5a. And now I'm going to do my equation of motion going up the slope for particle A. Probably need to have done something extra here. 2g cos 30, 2g sine 30. If you wanted to, you can draw that extra diagram. I probably would recommend you to do that. I'm going to stick with you though, Sufyan. What's the equation of motion for particle A? Okay. 2g. 2g sine 30. So if you find that hard, definitely draw out your second diagram. So you get 2 minus 2g sine 30 is equal to what? It's a smooth plane, yeah. Nope. 2a. So I've got my equation 1 and I've got my equation 2. Best way of solving those? Add them. Still always going to be an adding because you're always going to have one of the tensions is negative and one of them is positive. If you ever have it where the tensions are both positive or both negative, you're wrong. Okay? You've gone wrong. So I'm going to do equation 1, add equation 2. So I get 5g minus 2g sine 30 equals 7a. Now this is where you need to know these things off the top of your head. Sine 30, a half. So you've got 5g minus 2g times a half, which is, so that's 5g minus g. So you get 4g is 7a. So you get 4/7g is equal to a. Because 2g sine 30 is a half. So it's just saying a half of 2g is g, and 5g take away g is 4g. But look, they just wanted us to show that it was this, so I'm not actually going to change it to any number. I'm just going to leave it as 4/7g, and it's often okay to do that. Now we're going to find out what the tension is. Which equation is easier to find the tension? I think the second one. Yeah, because you've just got t, and you just add that to the other side. But either of them are fine. So I can then say that tension is equal to 2a plus 2g sine 30. Well, the acceleration is this, so double of this. What's double 4/7? So you've got 8/7g, and we said 2g sine 30 is just g. 8/7 plus that is 15/7, so you get 15/7g. Now that one we might like to put in newtons, and you get that it's 21 newtons when you calculate that. Now that's the easy part. I just want to, mostly I'm wanting to work on part C here because this is the stuff that's a bit new. State how you have used, let's just very quickly do part B. How have we used the fact that the string is inextensible in our calculations? There's no what, sorry? Yeah, it's the way we've used it is we've said that both particles have got the same acceleration. Because when we did the simultaneous equations, we were saying they both have the same acceleration. So how have we used the fact that the string is inextensible? We modelled both particles as having the same acceleration. So they're looking for same acceleration for that one. That's how we've actually used that in our calculations. If you said, I have used the fact that the string is inextensible by saying that the string is not stretchy, you haven't used that the string is not stretchy. You've just told me that the string is not stretchy. The way we've used it is we've allowed the accelerations to be equal. And then we're going to go to the interesting part of this question. We had to do all of that to get to this interesting part. We now want to calculate the magnitude of the force exerted on the pulley by the string. And this is the bit that's going to connect us up to the title, the resultant force acting on the pulley. Now, previously, I got you to imagine that you were a particle hanging from a rope. I got you to imagine that you were a particle with a rope coming out of your chest sat on a slope. Now, we're talking about what is the force that is being exerted on the pulley. So now I want you to imagine that you are the pulley. Okay, and you've got this pulley, you've got this string wrapped over you. What does it feel like if you've got this string wrapped over you? And you've all got a string wrapped over your own neck. So what does it feel like? Pardon? No, your lanyards, your lanyards. What does it feel like? Yeah, so actually, if I kind of do it, who wants, Hamza, put your arm out for a second. So if Hamza's arm is the pulley, and I've got, there's one of the weights is my hand, the other weight is my other hand, what does it feel like on your arm?
You're pushing me down.
Pushing you down. Does it feel like I'm pulling you exactly down like this?
No, that way.
It kind of feels like it's going at a sort of a direction, right? And the reason that it's doing that is because I've got one of the forces is pulling on his hand downwards. The other one is pulling slightly to the left. And so the overall force that Hamza was feeling was coming down in this direction that's like this. This is the normal, not the normal reaction. That is the resultant force of those two things. What was your arm having to do to keep steady? Yeah, his arm was pushing in the opposite direction to keep it steady. If his arm was totally weak and I was pulling on it like that, his arm would move exactly in this direction. So he's having to resist it by going in that other direction. This is what we would call the resultant force. What do you think we'd call this one? The normal contact force, the reaction. This is how he was reacting to me pulling on his arm like that. He was kind of resisting and going exactly in that opposite direction. So this one, we're not going to look at this today, but this is you could work it out easily. This is the reaction of the string on the pulley. It's the reaction, it's how the pulley is reacting to it. This is the resultant force. And I think Muhi sort of said this. What do we know about this angle here and this angle here? They're the same because it's acting exactly down the middle of it. And the reason that it's going to be exactly down the middle of it is because what do you know about this value of t and this value of t? It's the same because it's a smooth pulley and it's either side of the smooth pulley. So the example that we have is, I think it's 30 degrees down here, isn't it? And this is 90. So what's the angle at the top? 60. So when we slice that angle down the middle, it's a 30 and a 30. Now this is going to explain this thing that I've got here. When you have a triangle, and we're trying to come up with a general bit, if this is alpha, the one at the top is what? 90 take away alpha, because it's 180, take away 90, take away alpha, which is just 90 minus alpha. And when we slice it in two, you get 90 minus alpha, over 2. So this is this first part we've got here. It's the 30 that we have in this bit. Now I'm going to draw a diagram, and this time Hamza's arm is a dot. That's the pulley, okay? And we've got a force coming downwards like this, and we've got a force coming along like this. And both of these are tension. I'm keeping it as general as possible. And we are trying to find out what the resultant force is. Now I'm going to deal with each of them separately. I'm going to start off by dealing this one. We know the resultant force is going straight down the middle like this. So I'm going to resolve them in that direction. This T here, I can split into a force like this and a force like this. This T here, I can split into a force like this and a force like this. They're meant to be perpendicular. I haven't drawn that second arrow as perfect as I could have done, so let's have another go. What do we say this angle at the top was?
90 minus alpha.
Yeah, they're both 90 minus alpha over 2. What would be the size of this one that we have here? Using sine and cos, would it be the sine or the cos? Sine, because it's the opposite angle. So this one here is T sine 90 minus alpha over 2. And this one is T sine 90 minus alpha over 2. But they're going to cancel each other out, aren't they? Because they're exactly the same size. They're T sine 90 minus alpha over 2, and they're going in the opposite directions to each other. So I don't care about these. They've got nothing to do with me finding out the size of what I have here. But these ones, and this is where my diagram is getting a little bit complicated, one of those arrows is T cos, because it's running adjacent to the angle, 90 minus alpha over 2. But there's 2 of them. So that's why, because I have it times 2, that's why I end up with the overall resultant is 2t cos 90 minus alpha over 2, which is why I've got this thing written at the top here. So this is the most general kind of idea that you could have for it, right? That's the most general kind of one that you could have, 2t cos of 90 minus alpha over 2, where alpha is that angle that we have down here. But this is our question that we had. This is the question that we had up here. So let's actually finish off what part C says. Well, our diagram is up there, and it is 2t cos. What was the 90 minus alpha over 2 for our diagram, though? 30. Because that was the alpha. We're just saying, let's split that angle at the top, and it actually splits into a 30. And t, what was t from the previous slide?
21.
It was exactly 21. So it's 2 times 21 times cos 30. So that's 42 times cos 30, which is root 3 over 2. So it is 21 root 3, aka whatever 21 root 3 is on the calculator. 36.4 newtons. Now, I'm not sure, I remember this, but I'm a teacher who's taught mechanics for 8 years. So I obviously remember that. You are math students who have seen this for the first time. Pardon?
Equation sheet.
This is, no, this isn't in the equation sheet. Because really, it doesn't need to be in the equation sheet. Because Hamza, when he held his hand out and I put the rope around his arm, the lanyard, he knew that the force was acting exactly down the middle. So all you're really doing is working out what's the angle at the top. Well, when it was 30 here, it was 60, so they were 30. And the force we had here and here was 21 and 21. So actually running along there and running along there are both 21 cos 30s. Hence it being 2 lots of 21 cos 30. And we don't worry about this force or this force because they are equal and opposite and completely cancel each other out, right? So if you like memorizing things, that's something that can help you. But it's really important you understand why that works and how that comes up. So that's us done with forces, okay? That's us completely done with forces on this topic. We are going to do some questions from exercise 7F. These are challenging, and I want to make sure I see you doing some of these on the boards for me, okay?